Developer Education and Assessment in the Agent Era. This analysis reflects the education and certification landscape as of July 26, 2026. Introduction. Autonomous coding agents are changing software development from a task centered on typing code into one centered on specifying work, delegating tasks, supervising execution, and reviewing results. Modern coding agents can inspect a repository, develop an implementation plan, modify multiple files, run tests, respond to errors, and open a pull request for human review. GitHub's current documentation describes workflows in which developers assign issues to agents, monitor their work, request code review, provide feedback, and approve or reject the result. This creates a difficult question for education. If a student can ask an agent to produce a working program, what should the student be required to understand? The answer is not to abandon programming fundamentals. It is to change what those fundamentals are used for. Students still need to understand data structures, algorithms, programming languages, system design, security, testing, and debugging. However, they increasingly need to apply that knowledge to decompose ambiguous problems into manageable tasks, write precise specifications and acceptance criteria, provide useful context to coding agents, judge whether generated code is correct and maintainable, design tests that expose hidden failures, review security, privacy, performance, and architectural risks, coordinate several agents or tools without losing control, and explain and defend technical decisions. The next generation of developer education will therefore assess less of the student's ability to produce large amounts of code and more of the student's ability to understand, direct, verify, and improve software systems. The central shift from code production to engineering judgment. Coding agents are not simply faster autocomplete. Traditional coding assistants suggest a line, function, or small block of code. Autonomous coding agents operate at a larger scale. They can work across files, invoke development tools, execute tests, inspect documentation, and continue through multiple steps. That changes the unit of work. The developer's workflow increasingly looks like this. Understand the user or business problem. Define the desired behavior. Break the work into smaller tasks. Assign an appropriate task to an agent. Inspect the agent's plan. Let the agent implement within a controlled environment. Run tests and security checks. Review the result. Request changes or revise the design. Approve, merge, and monitor the software. The person who skips the planning and review stages may still produce code, but cannot reliably produce a trustworthy product. The limits of raw code output. Raw code production is becoming a weaker measure of ability because an agent can generate a large amount of plausible code quickly. At the same time, agents continue to struggle with long-horizon software evolution, multi-file changes, unclear requirements, and maintaining behavior across repeated modifications. One 2025 benchmark study found a substantial gap between agent performance on isolated issue resolution and more complex, long-term software evolution tasks. This creates an important educational distinction. A student who can generate code may not understand it. A student who can explain, test, challenge, and repair code demonstrates deeper competence. The educational target should therefore become validated software judgment, not simply successful code generation. How curricula are adapting. University curricula are moving toward comprehension and verification. The ACM, Institute of Electrical and Electronics Engineers, Computer Society, and Association for the Advancement of Artificial Intelligence's Computer Science Curricula 2023 report anticipated that generative artificial intelligence would change programming education. Its guidance suggests that students will need more emphasis on reading, comprehending, verifying, editing, modifying, adapting, and testing code. It also identifies problem decomposition as an area likely to become more important. The same guidance makes a crucial point. Even when an agent writes the program, the human remains responsible for determining whether the program is correct. This means that programming education cannot be reduced to writing prompts. Students need enough technical understanding to evaluate the output. The report also anticipates changes in software engineering education, including greater use of artificial intelligence for code generation, debugging, static analysis, and code review. Effective use of these tools requires stronger design and code comprehension skills, not weaker ones. Accreditation is beginning to reward broader engineering outcomes. The current computing accreditation criteria from the Accreditation Board for Engineering and Technology already emphasize analysis of complex computing problems, design and evaluation of computing solutions, professional communication, legal and ethical responsibility, security and privacy, social impacts of computing, a comprehensive project or experiential component. These outcomes are well suited to an agent-based development environment because they measure judgment and responsibility rather than keystrokes. As of July 26, 2026, proposed Accreditation Board for Engineering and Technology changes for the 2026-2027 cycle include additional artificial intelligence program criteria and a requirement that graduates be able to apply artificial intelligence theories, models, and techniques to complex problems. The proposed changes were still awaiting final adoption and were expected to take effect after the fall 2026 meeting, with first application during the 2027-2028 review cycle. The likely direction is clear. Programs will need to show that students can build and evaluate systems, not merely complete isolated programming exercises. New courses are teaching agent use as an engineering discipline. Several recent university courses illustrate the emerging pattern. The University of Maryland's 2025 course on effective use of artificial intelligence coding assistants and agents covered tools that can invoke build systems, run tests, and fix errors. It also addressed maintainability, architecture, application programming interface design, efficiency, scalability, security, continuous integration, code review, asynchronous agents, and automated code review. The University of Pennsylvania has proposed a sophomore-level computer science course focused on artificial intelligence-driven software development. Its proposed topics include delegation of coding tasks, modular design, scalable testing, risk management, reproducibility, collaboration, and ethics. The University of Michigan's Fall 2026 course, Applied Agentic Software Engineering, is even more explicit. It is organized into 3 phases: use coding agents effectively, build an agent using a large language model application programming interface, design, evaluate, and deploy an agent orchestrator. The course uses projects, laboratories, demonstrations, and checkoffs instead of traditional examinations. It states that grading will reward understanding over output and asks students to explain why an agent failed and how to fix the surrounding system. This is a significant design change. The course is not teaching students to produce code faster. It is teaching them to become technical supervisors of systems that produce code. How bootcamps are changing. Bootcamps are adapting more quickly than many traditional programs because their curricula are closely tied to employment requirements. However, the quality of adaptation varies. The dedicated artificial intelligence bootcamp model, Lewagen's current artificial intelligence software development bootcamp, combines full-stack development with artificial intelligence integration. Its published curriculum includes artificial intelligence-assisted coding, large language model integration, production deployment, retrieval augmented generation, and autonomous artificial intelligence agents. This model treats artificial intelligence as a thread running through the program rather than as a single optional lesson. Students are expected to learn both: how conventional software systems work, how to use artificial intelligence tools to build and operate those systems. That combination is important. A learner who only knows how to operate an agent may be unable to recognize a flawed architecture. A learner who only knows conventional programming may not be prepared for modern development workflows. The Add an Artificial Intelligence Unit model, Springboard Software Engineering Bootcamp, retains a conventional foundation in web development, application programming interfaces, front-end development, back-end development, and full-stack projects, while adding an artificial intelligence unit focused on prompt engineering and collaboration with generative tools. This model is useful for learners who need strong programming fundamentals first. It also reflects a practical reality. Many students should not begin by building autonomous agents. They should first learn how software works, how to use version control, how to read error messages, and how to test a program. The weakness is that a short prompt engineering module can become too shallow. A serious agent-era curriculum should teach more than how to ask for code. It should teach how to create a repository context file, how to write a technical specification, how to define task boundaries, how to constrain an agent's permissions, how to inspect agent plans, how to evaluate generated tests, how to detect security problems, how to compare alternative designs, how to document agent involvement, what bootcamp students should look for. Prospective students should ask whether a program assesses the following. Can students explain code they did not personally type? Do students review and repair flawed agent output? Are tests, security, and maintainability graded? Is there a live demonstration or technical defense? Do students maintain a version-controlled project history? Are students taught how to work without an agent when needed? Does the program teach product discovery and requirements analysis? Are tool-specific skills balanced with durable engineering principles? A program that advertises build an application in 1 week with artificial intelligence may be excellent for rapid prototyping, but that is not the same as preparing someone for professional software engineering. How certifications are adapting. Certification providers are developing 3 broad types of credentials. Tool-specific knowledge certifications. The GitHub Copilot certification from Microsoft assesses responsible use, Copilot features, data architecture, context and prompt crafting, developer productivity, privacy, content exclusions, and safeguards. The examination is proctored, lasts 100 minutes, and may contain interactive components. This credential recognizes useful workplace knowledge. It can show that a person understands how to use a particular development platform responsibly. Its limitation is that it is strongly tied to one product. A professional who knows how to operate GitHub Copilot may still lack the ability to decompose a complex product requirement, challenge an architectural choice, or review a security-sensitive change. Platform-based artificial intelligence development certifications. The AWS Certified Generative AI Developer professional certification is broader. Its examination guide includes foundation model integration, data management, compliance, implementation, agentic artificial intelligence solutions, security, governance, testing, troubleshooting, monitoring, and optimization. However, the examination is primarily multiple choice and multiple response. It is a substantial knowledge test, but it does not fully demonstrate whether a candidate can build, review, or defend a working system. This illustrates a broader problem. Knowledge examinations are easier to scale than performance examinations. Certification organizations can test terminology and design principles efficiently, but practical competence requires an environment in which candidates must make decisions and deal with failure. Lab-based and project-based credentials. Microsoft Applied Skills credentials provide a more promising model. They require learners to complete interactive tasks aligned with real work in a lab-based assessment. Microsoft positions these credentials as evidence that a candidate can solve real cloud and artificial intelligence challenges, rather than simply recall information. Carnegie Mellon University's Executive Education Agentic Artificial Intelligence program combines live teaching, guided laboratories, assignments, multi-agent workflows, evaluation, guardrails, logging, observability, and a capstone project. These programs are not identical to independent professional certification, but they show the direction credentials are likely to take. Shorter practical assessments, sandbox development environments, realistic repositories, evaluation and observability tasks, capstone systems, oral or recorded technical explanations, evidence of responsible tool use, assessment techniques that measure understanding. The best assessment strategy does not ban agents from every assignment. It uses agents where they reflect professional practice and reserves some activities for measuring independent understanding. Specification and decomposition documents before writing code require students to submit the user problem, functional requirements, non-functional requirements, assumptions, constraints, data structures, interfaces, acceptance criteria, a task breakdown, known risks. The document should explain why the problem has been divided into particular tasks. This measures whether the student understands the problem before asking an agent to implement it. Agent planning checkpoints require students to show the agent's proposed plan before implementation begins. The student must identify which parts of the plan are acceptable, which parts are incomplete, which assumptions are unsafe, which tasks require human approval, which tests should be added. The final grade should reward the quality of the student's judgment, not the length of the agent's plan. Code review assessments give students an agent-generated repository containing deliberate defects. The defects can include incorrect edge case handling, insecure authentication, poor error handling, hidden performance problems, duplicated logic, unclear interfaces, inadequate tests, privacy violations, dependency risks. Ask students to produce a review with severity levels, evidence, proposed fixes, and regression tests. This is closer to professional software work than asking students to create another small application from scratch. Explain back and oral defense. A student should be able to explain what the system does, why the architecture was chosen, which parts were generated, which assumptions the agent made, how the tests demonstrate correctness, what could still fail, what trade-offs were accepted. A short oral defense can be conducted individually or in small groups. It does not need to be intimidating. 5 to 10 focused questions are often enough to reveal whether a student understands the submission. Transfer tasks. After a student completes an agent-assisted project, provide a new requirement that cannot be solved by simply repeating the original prompt. For example, add a new data source, change the performance target, support an unexpected input format, remove a dependency, add access controls, explain a failing test, refactor a module without changing its behavior. The student may use an agent, but must explain the plan, verify the changes, and defend the result. Transfer tasks measure whether the student learned a general method rather than memorized a successful interaction. Test design and adversarial testing. Students should be graded on the quality of their tests, not only whether the generated code passes provided tests. Useful requirements include: write boundary tests, create negative tests, test invalid input, test failure recovery, check performance assumptions, use property-based tests where appropriate, test security-sensitive behavior, explain what remains untested. The key question is not did the code pass, but did the student know what needed to be tested? Version history and process portfolios. A project portfolio can include initial specification, task decomposition, agent plans, major prompts or instructions, commits, test results, review comments, failed approaches, design changes, final reflection. A process portfolio should not become a requirement to submit every line of private conversation. A representative record is often more useful than an enormous transcript. Princeton's 2025 programming course, for example, permitted generative artificial intelligence tools, but required students to describe their use in a README file through a representative summary rather than an exhaustive transcript. Structured peer review. Peer review turns students from only being code producers into code critics. Early research suggests that rubric-based peer assessment can approximate instructor evaluation with moderate accuracy while developing evaluative thinking and engagement. Students should be required to justify their comments with evidence. This code is bad is not a review. This function performs a database query inside a loop, creating a likely performance problem when the collection grows, is a review. Prompt and specification problems. Prompt problems are programming exercises in which students write natural language instructions that cause an artificial intelligence system to generate code satisfying a specification. The approach explicitly teaches students to communicate computational requirements to code-generating systems. This can be useful, but it should not be the only assessment method. A 2026 study involving more than 900 students found that common errors included omitting important details from prompts. When generated code failed, students often focused on clarifying their intention rather than tracing the code or examining test cases. Prompting can therefore reveal decomposition and communication skills, but it must be combined with code reading, testing, debugging, and review. A sample assessment structure. A practical project could use the following weighting. For the full table, please open this article on easy coding tools. This structure still rewards a working product, but it prevents a student from receiving a high grade merely because an agent produced a large codebase. Academic integrity. In agent-assisted coursework, blanket bans and unrestricted use are both inadequate. A blanket ban may be appropriate for a specific foundational assessment, especially when the learning objective is independent programming practice. However, a universal ban is increasingly difficult to enforce and may prevent students from learning tools they will encounter in professional work. Unrestricted use is also inadequate. If students can submit agent-produced work without explanation, the assessment may measure access to a tool rather than learning. The strongest approach is explicit assignment-level policy. 3 useful policy modes. Mode 1. Agent prohibited. Use this for examinations, foundational programming drills, individual debugging demonstrations, core algorithm exercises, assessments designed to measure unaided recall or implementation. Carnegie Mellon's Principles of Imperative Computation course prohibits artificial intelligence tools for any part of graded work, including generating solutions, explaining solutions, formatting code, and generating test cases. Mode 2. Agent restricted. Use this when students may ask for concept explanations, documentation help, error message interpretation, library or application programming interface clarification. Brainstorming. Critique of a student-created design. Minor refactoring. Carnegie Mellon Systems courses allow artificial intelligence tools for understanding application programming interfaces, libraries, frameworks, provided code, and error messages, while prohibiting requests for partial or complete assignment solutions. Mode 3. Agent permitted with disclosure. Use this for realistic software engineering projects. Require students to disclose which tools were used, what tasks were delegated, whether generated code was copied, modified, or rewritten, how the output was tested, what the student learned, which parts of the design remain the student's responsibility. Princeton's scholarly integrity guidance states that permitted artificial intelligence use must still be disclosed, and that representing generated output as one's own or failing to disclose its use can constitute an integrity violation. Harvard Graduate School of Education similarly allows uses such as clarification, brainstorming, and exploration, while prohibiting students from submitting artificial intelligence-generated coursework as their own. It also requires documentation of permitted use and warns that students remain responsible for accuracy, privacy, copyright, and bias. A practical disclosure statement. A course can provide a simple template. I used tool name for planning, debugging, code generation, testing, documentation, or review. I delegated specific tasks. I reviewed and modified the output, tested the resulting system, and remain responsible for the accuracy, security, and originality of the submission. Students should not be required to disclose ordinary spelling correction in the same way as delegated implementation. Policies should distinguish between minor assistance and substantial cognitive or technical contribution. Privacy and equal access institutions should provide approved tools or alternatives. Students should not be required to upload confidential coursework, personal information, unpublished research, or proprietary code to public systems. UNESCO's guidance calls for a human-centered approach that addresses privacy, safety, equity, inclusion, and institutional preparedness. Courses should also consider students who cannot afford several paid tools. A fair course can provide a shared institutional tool, offer a local or open-source alternative, design assignments that do not depend on one vendor, grade reasoning rather than access to the most powerful model, allow non-agent pathways for every essential learning outcome. Practical methods for incorporating agents productively. Use a controlled repository. Give students a repository containing a clear README file, a small but realistic codebase, automated tests, a continuous integration workflow, a list of known issues, a style guide, a security checklist, a changelog. This makes agent use observable and gives students something more realistic than a blank coding exercise. Require a plan before implementation. Students should not begin by asking an agent to build the whole application. require a sequence. Ask the agent to inspect the repository. Ask for a summary of the architecture. Ask for risks and missing information. Write the student's own task plan. Approve one small implementation task. Review the resulting changes. Run tests before continuing. This teaches controlled delegation rather than blind delegation. Use an agent team with clear roles. A simple orchestration pattern can include: planner proposes the task breakdown, implementer modifies the code, tester creates and runs tests, reviewer searches for defects and risks, human evaluator approves or rejects changes. Students should learn that adding more agents does not automatically improve quality. More agents can create contradictory instructions, duplicated effort, increased cost, and unclear responsibility. The educational goal is not to build the largest multi-agent system. It is to choose the simplest workflow that produces trustworthy results. Build in human approval gates. Require explicit approval before an agent can. Change authentication. Modify data schemas. Add dependencies. Access production systems. Change deployment configuration. Delete files. Merge a pull request. This teaches students that autonomy must be bounded by permissions and review. Grade failures deliberately. Agents are most educational when they fail in informative ways. Instructors should include ambiguous requirements, conflicting constraints, incomplete tests, security-sensitive operations, misleading documentation, flaky tests, performance limits, a change that appears correct but breaks another feature. The student's task is to diagnose the failure and improve the process. A competency framework for 2026 to 2031. The following framework is designed to remain useful even as specific tools change. Domain 1. Technical foundations and code literacy. A competent developer can read unfamiliar code, explain control flow and data flow, understand interfaces and dependencies, analyze algorithmic complexity, use version control, debug without relying entirely on an agent, evidence, code explanation, manual debugging task, design critique, and individual transfer exercise. Domain 2. Problem framing and decomposition. A competent developer can clarify user goals, identify constraints and assumptions, separate essential from optional requirements, break work into independently testable tasks, define acceptance criteria, recognize when a task is too broad for reliable delegation, evidence, specification, task graph, risk register, and explanation of decomposition choices. Domain 3. Agent direction and context engineering. A competent developer can provide relevant repository context, give precise instructions, define boundaries and permissions, choose when to use an agent and when not to use one, compare alternative plans, recover when the agent follows the wrong interpretation, evidence, planning checkpoints, representative interaction records, and a live revision task. Domain 4. Verification and review. A competent developer can inspect generated code, design meaningful tests, identify hidden assumptions, review security and privacy risks, evaluate maintainability, explain what the tests do not prove. Evidence, code review, adversarial tests, defect finding exercise, and oral defense. Domain 5. Orchestration and operations. A competent developer can coordinate planning, implementation, testing, and review tools, use checkpoints and human approval gates, track cost, time, and tool behavior, maintain reproducible workflows, observe failures and improve the system, decide whether multiple agents add value. Evidence, working orchestration workflow, logs, evaluation report, and cost or performance analysis. Domain 6. Product and systems design. A competent developer can select an appropriate level of automation, design modular systems, balance speed, quality, cost, and risk, connect technical decisions to user outcomes, recognize when a simple non-agent solution is better. Evidence, product brief, architecture decision record, prototype, and user-centered demonstration. Domain 7. Responsible professional practice. A competent developer can disclose artificial intelligence assistance, protect private and proprietary information, respect copyright and licensing obligations, identify bias and reliability risks, communicate uncertainty, accept responsibility for the final system. Evidence, disclosure statement, risk assessment, privacy review, and professional presentation. Suggested proficiency levels. For the full table, please open this article on easycoding.tools. By 2031, a professional credential should demonstrate movement through these levels, rather than simply confirm familiarity with a particular software tool. Recommendations for different stakeholders. Universities add agent-aware software engineering modules to existing courses. Preserve foundational programming and algorithms. Replace some code generation assignments with review and transfer tasks. Require students to explain and defend important work. Train faculty in agent tools, evaluation design, privacy, and integrity policy. Build shared repositories and sandbox environments. Boot camps teach conventional development and agent-assisted development together. Make testing, architecture, and security central parts of the curriculum. Require portfolio projects with process records. Add live technical demonstrations. Teach product discovery and requirements writing. Avoid promising that prompting alone creates job-ready engineers. Certification providers increase the use of lab-based assessments. Include code review, testing, debugging, and threat analysis. Use realistic repositories rather than isolated multiple-choice questions. Test tool-independent judgment. Add short oral explanations or recorded demonstrations. Refresh content frequently without making the credential dependent on one vendor's interface. Instructors state exactly what is allowed for every assessment. Design assignments around the intended learning outcome. Give students approved tools or equivalent alternatives. Assess process, reasoning, and verification. Use logs as evidence, not as the only proof. Avoid relying on artificial intelligence detection software as the primary integrity mechanism. Learners and product creators learn enough conventional programming to read and challenge generated code. Start with a small product rather than a vague large application. Write the specification before opening an agent. Delegate one issue at a time. Review every change and test every assumption. Keep a record of important decisions. Treat the agent as a fast junior collaborator, not as an unquestionable expert. The first next step for someone beginning a product creation journey, the most useful first step is choose one small user problem and write a one-page specification before asking an agent to write code. Include who the user is, what problem they have, what the first version must do, what it must not do, 3 acceptance tests, 1 important security or privacy concern, 3 small implementation tasks. Then ask the agent to review the specification and identify missing requirements, not to build the entire product. After correcting the specification, delegate only the first task. Review the proposed plan, inspect the changes, run the tests, and write down what the agent got wrong. That single exercise teaches the most important lesson of the agent era. The quality of the result depends less on how much code the agent can produce than on how clearly the human defines, supervises, and evaluates the work. Conclusion: developer education is moving toward a new balance. Students will still need to write code, especially while learning foundational concepts. But professional competence will increasingly be demonstrated through problem decomposition, specification, code comprehension, review, testing, orchestration, product judgment, and responsible use of autonomous systems. The strongest curricula will not treat coding agents as either cheating machines or magical tutors. They will treat them as powerful but fallible engineering tools. Students will learn when to use them, how to constrain them, how to evaluate their output, and how to take responsibility for the final system. The most durable developer of the next 5 years will not be the person who can produce the most code by hand or generate the longest prompt. It will be the person who can turn an unclear goal into a reliable process, guide several tools toward that goal, detect failure early, and explain why the resulting software deserves to be trusted. All links to sources are available in the text version of this article. You can find the full article at easycoding.tools.blog. Thanks for listening. For more practical AI coding guides, tool comparisons, and resources for builders, visit easycoding.tools. And if it's easier to remember, just go to aibuilds.it. It redirects to easycoding.tools.